So with that.
Thank you, Sunil, for that kind introduction. I've actually known people here for almost 3 decades, but this is my first trip. Bharat and Ahmed I have known for, Bharat actually for more than 30 years. I met him the first time in summer of '81, believe it or not, when I was still a grad student at UT Austin. And Ahmed I must have met a few years after that, since we are all about at least he and I are about the same age. It's kind of out of the way to get here, so it doesn't happen too often that I go to places that I don't otherwise visit for, IBM Research or some conference or the other. But I'm very happy that I'm here, and I didn't even know about Purdue being the oldest institution in America to have started the computer science program. I mean, I'm an old guy too, so I guess I qualify on that count. I was just posting the other day on Facebook, it's been 39 years since I started using a computer. As an undergrad at IIT Madras, in my second year is when they first got a computer at all, and it happened to be a 3rd generation, almost top of the line model of the IBM mainframe, which was a gift from West Germany, and punch cards and 256K memory. So don't complain about, a few gigabytes not being enough in your real memory. It was core memory, 256K, and then it became 512 and all that. So, but we are going to talk about this stuff here. So almost 50 years, if you see the time frame here. You had all these pre-relational systems like IMS and airline control program, which now is called Transaction Processing Facility, which is the software that is behind things like Sabre airline reservation system. So people who think that all this, relaxed consistency and all that is a new thing that the Web 2.0 crowd created, nothing can be farther from the truth. That ACP or TPF already had these notions. For instance, they said, we are not going to bother with strict ACID kind of properties, which of course came up later, because they said performance is primary importance over there. So they didn't even have a proper log and all that to do recovery. They had sort of loosey-goosey semantics and such, because they were trying to have the highest possible throughput. And they ran on a bare machine, and they did even share disk architecture in that thing. The locking was done in the disk controller, believe it or not. And they said, well, if your reservation is lost and you complain about it, they give you a free ticket and you're happy and they are happy that they got better performance, not worrying about, very strictly thinking about data consistency and such. Of course, that wasn't used for your bank account maintenance and such, because then the federal government would have been after them, because you can't be loosey-goosey about, even a few cents here and there. Although, you know that the banking people have done all sorts of fraud and all that. So, there's going by the book versus all this hanky-panky, a la 2008 kind of time frame. Then, of course, I happen to come from IBM Research, the same department where Ted Cord used to be there. He was still there. Elisa, by the way, I know for almost 30 years. She joined the same project that I joined 30.5 years ago. She joined exactly 30 years ago, as she told me this morning. July of '82 is when she came as a postdoc / visiting scientist to the R-Star distributed database project, which you see there listed, distribution. And my first manager is the mother of cost-based query optimization, Pat Selinger. She started the R-Star project and later became a fellow and all this kind of stuff. She also got the Sigmod Innovation Award and so on. So you can sort of look at what happened, and Don Chamberlain was down the corridor from me, one of the fathers of SQL. Unfortunately, the other guy died soon after the work was done in an accident. So the System R project, which happened in parallel with Ingress project at Berkeley, which was led by Stonebreaker, these were the pioneering projects of that time, which resulted in a whole lot of transactional stuff, query optimization stuff, authorization kinds of things coming out. So they then, of course, spawned a whole industry. Oracle's whole existence is thanks to the IBM Research people who wrote papers where they detailed quite a bit the semantics and the syntax of SQL. And so Oracle released its product even before IBM product people who are happy with IMS's success and so on. They said, why rock the boat, confuse the customer by releasing something called relational system? And so we are still paying the price of not having been there first, especially on the non-mainframe platforms. We let that market be taken over by Oracle, Sybase, Informix, and so on. But over the decades, the focus has shifted to having extensible database systems. We had the Starburst project. Around the same time that Exodus and such projects happened at Wisconsin and other places. And then you had all this development of multimedia data set type support with cartridges, extenders, and so on. Informix, Oracle, and IBM products had these specialized functions to support video, audio, and such. That market didn't really take off as much as we all thought it would. Informix guys went and paid a ton of money to Stonebreaker and Company and bought Illustra technology, which was a commercial version of Postgres, and that didn't result in a whole lot of money coming to Informix. And then, of course, federation became a hot topic. IBM released, what did we call it, Data Joiner, which didn't actually come out of research. The product guys did it initially. And then we had the Garlic project that Laura Haas started, which was one which tried to automate, in some fashion at least, the development of support for different data sources by having the notion of wrappers, which can then give you a more uniform view of heterogeneous data sources so that the integration can be done more easily using more traditional, if you like, distributed database technology. And meanwhile, of course, as I think Dave Dewitt had a paper, Roadkill on the Information Superhighway, I think was the title of his keynote at VLDB. He basically said, look, we database people messed up. We didn't pay attention to all this web-related stuff. So the web world took off on its own without necessarily employing databases as the repository for the web information. And he thought that if we don't get our act together and do stuff that's relevant in the web age, we may become irrelevant because they all started using the file system directly rather than relying on a database system for storing your HTML pages and such. And of course, more recently, you have even a more dramatic thing happening with the Web 2.0 crowd coming into the picture, Google, Twitter, Facebook, and so on. And they found database systems, namely relational database systems, to be too heavy duty or not flexible enough in terms of the schema restrictions and such. So they decided to go the route of the so-called NoSQL systems, as well as, in the interest of making things cheap, trying to employ Intel class machines, commodity hardware, with local disks rather than SAN attached, fancy disks and such. And in that context, they felt the volume of data that had to be managed and the kind of failures that they had to deal with had to be given more importance than the sorts of things that most of us in the database community were worrying about. And so they then went off, in many ways, the deep end by creating chaos. Right now, there is tremendous amount of chaos. All this hard work that went into standardizing on SQL and such, or even the general notion of having standards for interoperability and all that, people seem to have short memories about the benefits of such things, or the benefit of having high-level languages as a way of letting the users describe what they want and letting the system then go and figure out how to get the information they want, and letting the system worry about the optimization aspects. That again has been thrown out. It's like baby with the bathwater kind of thing. And so now some of these people would like you to believe that by being empowered, by being asked to be the query optimizer yourself, because they give you a very low-level language to program in and not give you a high-level language, you should feel happy that you are being empowered. I mean, give me a break. So all these NoSQL systems have their own APIs. There is no commonality and such. And so it's one thing for the Googles and the Facebooks of the world to have smart-ass people within their companies with PhDs and all this kind of credentials who can do anything they want and mess around with the nerds of open source software and such. And it's another thing for regular company people to think that they can pull off the same thing. But it's gotten to a stage where it's become a fashion statement. You know, if you say you're not working on this topic, you are these gray-haired guys who are the old world guys and who are not willing to move with the times and so on. So even in big companies, as a result, you find even enterprises, Wall Street and so on, even China, where I was last week, the youth especially, as well as the ones who don't want to feel left out amongst the more mature people, they all think they have to join this bandwagon. A lot of the requirements may be legitimate, but not necessarily the approach taken to solve it, where the innards don't have to be all that different between a relational system and these NoSQL systems, even if the data modeling requirements and other considerations like scale and failure tolerance and so on. But people seem to think just because the higher level things are different, that gives them a license to go off the deep end and do whatever they want. And for a while, there is so much hoopla that they can get away with it. But I think once these things become more mainstream in the sense of people becoming dependent on it, on things that have stringent requirements compared to, if you're asking a query on the web, you're willing to take almost anything as an answer because there is no right or wrong answer for a lot of those things. So those sorts of things don't cut it when you are in a different kind of domain. And so we are in that stage where, it's still, I would say, experimental in spite of millions of dollars being invested in a lot of these startups like MongoDB and such. You can't take that itself as a validation that this is all for real and it has longevity. By that token, a lot of the nonsense that happened during the dot-com era, where billions of dollars were invested and then it all went kaput, should be a lesson. Again, people seem to have short memory. They don't want to necessarily, when the going is great, when there is so much sheep mentality, everybody wants to join this bandwagon. And so I would say take with a grain of salt all the hoopla that's there. I blogged for a few times on this NoSQL hoopla, what's nonsensical about it, and the nonsensical, I made it SQL. So go read it and you'll see more validation of the major points I'm making here. This is just some, past kinds of things. So encryption and such became very important. We are still introducing lots of functionality in the encryption as well as, what's the other one? The related topic. You want to make it smaller? Compression, thank you. So those are, especially in the context of big data, the amount of disk space that's being taken up has become the dominant factor in terms of overall installation cost. And so compression is a big thing. And we have a project going on at IBM Research where we try to do as much of the things possible in the compressed form, query processing and such. This is the, what's the name these days? We keep changing names of our products and such. So this is the project that Guy Lohman and company are working on. We had a name for it when it was originally a research project, then it got commercialized under a different name. I'm not going to get it now. And of course, you also have now the HANA work being done at SAP, which is an in-memory database technology that's getting a lot of visibility, and SAP is pushing it like crazy. One of their founders, He even has an institute now at Potsdam where a lot of this stuff is getting researched on and such. Hasso Plattner is the guy who used to compete with Ellison on sailing, for instance. So he's really big time behind this. And there is also quite a bit on in-memory exploitation with large amounts of memory becoming available. Not just DRAM, people are now pushing on trying to use even SSDs, and going forward, which will be the later topic, storage class memories, one form of it being phase change memory. Of course, HP is pushing on a related thing called memristors. What else? Federated access. Analytics, of course, is a big growth area. IBM spent the most it has ever spent on acquisitions for a single company, $5 billion, acquiring Cognos. And we have since then acquired other companies which are in the analytics space, like SPSS, which is a competitor to SAS, as well as iLog. And so that's one of the 4 big areas that IBM has declared very publicly will be fueling our growth, going from $10 per share earnings in 2010 to $20 per share by 2015. This was a publicly stated thing in 2010. Various forms of analytics people are working on these days, not just explaining what happened, but even trying to predict what will happen. So predictive analytics is an important area. In this context, one of the major stumbling blocks has been the fact that a lot of these statistical packages that have been available, SAS, SPSS, and so on, have traditionally required smart-ass people to be around to use them, people with PhDs in statistics kind of thing. So with the wider adoption of analytics, it's well recognized that even if you're willing to pay such people, there aren't enough of them to go around. And so you need to make these things usable by ordinary human beings. Ordinary being, even us regular computer science type of people rather than statistics kind of people. So that's an area that is also something that is getting affected by the increased amount of data that's text-oriented with web pages and such, right? Social media and so on. So text analytics in particular, more so than traditional structured data analytics, has become a big growth area, and hence the renewed interest, if you like, with respect to people with machine learning and such background, rule-based systems and so on, AI-ish kind of people, let's say. So math has become more fashionable again, if you like. All sorts of optimization issues that used to be originally, let's say in the T.J. Watson Research Center, the math science department people who worked on crew scheduling, airline scheduling and such with American Airlines and such people, integer programming, linear programming and so on, they are all now in much greater demand as analytics takes off. And so they are now becoming also more and more domain experts. So that's the other thing that you need to worry about. So not just straightforward computer science kind of background or statistics background, but becoming more knowledgeable about individual domains as companies like IBM also move up the food chain, go from just providing tools and such as in the past, hardware as well as operating systems and middleware, to providing solutions. And as we talk about, as you might have noticed in commercials on Smarter Planet and so on, you need to think about learning about specific domains like transportation, distribution, whatever the sectors might be. And this also brings up the point about how sensors and such have become very important. As you are trying to, monitor traffic or deal with pollution levels and such, or mobile computing with, smartphones and such, this whole space of large amounts of data coming from Mickey Mouse devices has become more important. And the volume of data is high, and the speed at which it's coming is also high, as well as what IBM is now calling veracity, which is the indefinite nature, meaning may or may not be accurate kind of information. These sensors, even RFID readers and so on, can make a lot of mistakes. And so all your observations cannot be taken as God's truth or whatever. So you need to be willing to account for the fact that some of this may be doubtful and such. So you might have to model the likely erroneous nature of the data and such. So visualization is another area, by the way, with all this analytics that's become an important topic. Let's see, I'm told that I'm running out of time for this main stuff I'm supposed to talk about. But just to sort of emphasize the point, we've sort of come full circle now in many ways, meaning we used to have more imperative-oriented programming languages with some embedded imperative kind of query languages being there, like DL1 and IMS, and codicil-oriented network database systems. And we then went to this higher-level language like SQL. Quell was the ingress one, which didn't win the battle between IBM and Berkeley, let's say, which Stonebreaker still cannot forget that Quell didn't win against SQL because he felt that language was cleaner and all that. Then we went to XML, which already sort of was going back in many ways in the sense of, at least the model-wise, it was going to network and hierarchical kind of data models from a flat relational model. And now even with the query language, we've gone to the DL1 kind of era because of all this NoSQL stuff taking off. Okay, so of course, there are other aspects that are different now. There's parallelism and exploiting all sorts of new hardware technologies and multi-core and on and on. On those aspects, yeah, there is progress. But in some of these other aspects, you could think of it as regress, which is not too different from the way when we had session-oriented ways of doing things in distributed systems and so on. Then came HTTP with this, every interaction is like a new interaction. There's no memory on the other side and such. That worked as long as you were looking up information, but the minute you wanted to do anything transactional and so on, you had to have a context that's still there. You can't keep going from one server to another server on every interaction. Your shopping cart, what's going to happen to that? Locks are held and you need to go back to that same place to release the lock. So then we started introducing all this, hidden parameters in your URLs and cookies and such as a way of trying to now retrofit into the memory-less interactions some memory-oriented things. So in a similar sense, the people who threw the baby with the bathwater with all this NoSQL stuff are now ever so slowly bringing back those features of relational that they thought were not needed or were too much in the way in terms of performance or whatever the excuse was. Now you find that they are shoving on top of NoSQL systems or Hadoop and such systems, higher level query languages. And of course, if the base is very flaky, then you're going to pay the price of patch over patch instead of from the beginning thinking of ultimate requirements and building a strong foundation. Same thing with MongoDB and such. One lock for the whole database in a node. Give me a break. You don't need to do any modeling, any measurement to realize that's not going to cut it, especially with all the multi-core kind of scenarios where the degree of concurrent executions is going to be much higher than in the days when System guys invented traditional locking and so on. So there's some of this going on, and hopefully we all won't crash and burn with some of these recent developments. And in the interest of scale and such, when they talk about scale, they don't think of concurrency scaling. For whatever reason, they think that having 1,000 machines chewing on your data for a single job is more exciting than thinking about some of these other aspects to scaling that they conveniently forget. So content management and such, there's a whole bunch that one can spend talking about all this. Let me see if there is anything specific here. That the mainframes, by the way, are not dead. In case you doubted, there was an article in the New York Times on Monday which talks about some of this. Of course, the growth of information has been fueling a lot of the sales of disk drives. So EMC and such guys, as well as IBM, we are not in the disk hardware business, but we are still in the disk software business, just like EMC is. That's been fueling a lot of the money making in the storage arena and fueling all these new developments. By the way, we are still working on tape hardware in IBM. We only sold the disk hardware business. And denser tapes are still being made by IBM and making tons of money. And there's even fancier stuff that's in the works at my lab. And so that's, by the way, not dead. So anyone who thinks that anything that happened before, you can forget about it, that will disappear. Tape hasn't died because the disk hardware came and so on and so on. So there's all this, petabytes of data and exabytes of data being very casually talked about. Petabytes are now very common, by the way. So even in India, the Bharti Airtel company has multi-petabyte database of its warehouse data, call records and such. So let me see, what else do I want to say? Of course, this ETL business has become a big business, especially because of these veracity problems that I mentioned before, and probabilistic databases and such. Okay, XQuery, by the way, this is an area where we spend a lot of money. None of the vendors, I think, has made enough money given the investments that went into XQuery, the XML query language, which is a standard, and we enhanced DB2, Oracle enhanced its system, so did Microsoft's SQL Server. That hasn't, from a pure adoption sense, taken off as much. Or DBMSs, which at one time some people thought would take off, didn't take off, but then they sort of recast themselves as the cache managers in a J2E kind of environment, because the programming language deals with persistent objects in the object form, but the persistent store was relational, and so there was all this OR mapping that used to happen, object relational mapping. Now those guys are also recasting themselves, the ODBMS guys, object-oriented database guys, as one of these key value stores. Everybody now calls themselves a key value store. And then there are even attempts to shove on top of a relational system a more flexible data modeling capability, like being able to store JSON objects, for example, which is one of the selling points, by the way, of MongoDB, that they can natively store JSON objects. So now relational guys are saying, what the heck, I'll also provide that. After all, with all this XML extension and so on, I can shove anything into a single column. And I have the query language also to go get at parts of it anyway. So it's now a matter of extending that to deal with a different kind of object than what the XML model supported. So, okay, I think I should get out of this, because otherwise, let me just quickly see whether CPU trends, well, so this might be an interesting thing to know about. Look at this, the way things have changed, right? 6 cycles to access memory, 200 cycles to access memory now. You will see a slide later on in my other presentation, which gives you a more real-world feel for what the different access times are, and how, if you translate to real-life kind of time measurements, it will hit you. But this whole business of cache hierarchy and how to make use of it and all that has become big business. And so there are all sorts of developments in the database community, Natasha, Ilamaki, and various people like that, Jun Rao, who talked about in their PhD thesis how to design database structures, column stores, and such, in order to take advantage of the hardware features, so that you can be more efficient in the way you process your predicates and take advantage of compression kind of facilities, how FPGAs have a role to play, how GPUs can be leveraged to make things happen faster, especially when you're dealing with vast amounts of data and so on. So it's in that sense that this community is very alive and everything. Of course, as technology keeps changing, what might have been a good thing to do at one time may not anymore be a good thing to do, because its advantages have been taken over by somebody else. But in many ways, 30 years ago, well, I should say even 35 years ago, before I came to America, in the like early to mid 70s, database machines were very popular. At University of Toronto, they had a relational array processor. In University of Florida, they had a CASM system, and I think ICL in the UK had its own thing, content addressable file system or something they called it. And then sort of all went by the wayside because all that specialized hardware development was becoming too expensive. So then commodity things took over. But then now we are discovering that some amount of this kind of specialization of hardware functionality is useful as long as you are able to develop that hardware functionality without having to invest billions of dollars in new chip designs and such. So you find now in a different garb, namely appliances, these things have come back. And so appliances are a big deal now, not just from a performance kind of viewpoint, but also from the viewpoint of installing and getting going with it much faster than buying separately the hardware and the software and installing them and installing the operating system as well as the middleware and such. So from a usability perspective, things like IBM's acquisition called Netezza, which leverages FPGAs, as well as Oracle with its initially HP-based but subsequently Sun-based Exadata, Exalytics, and all these sorts of products that they have released. I don't know what Microsoft is up to, but they've also acquired a couple of companies, and so in due course of time, who knows, they might come out with some kind of an appliance. So those are some of the other things that have caused, if you like, hardware and software people to come together. And so that's something to keep in mind. So having said that, let me now switch to the other presentation. I changed the title, but it looks like I forgot to add it here. I made it hardware and software architectures. As you will see, there's a fair amount of discussion about the implications of these sorts of memory technologies, even on the hardware architectures. You can find, by the way, this presentation on my webpage, so it's easy to go see that. It's been a fairly lengthy effort. I used to be the IBM India chief scientist for almost 3 years. At the end of that assignment, when I came back to Almaden, was around the time when this project was started by another guy who had come back from China. He used to be in our product organization, but he joined research for the first time, Yun Wang, who is now back in China. So this is IBM research-wide effort to look at all the implications of hardware as well as software in the what we call storage class memories. There are groups in Almaden, Yorktown Heights, T.J. Watson Research Center, our headquarters, and also in IBM Zurich, as well as IBM Austin, where we have the Austin Research Lab. People are working on these things. But if you want to get more into it, there are a few things that are listed here. One of the things you'll see there is a paper that the Microsoft guys had in SOSP, Symposium on Operating Systems Principles, where they discuss file system design that's intended to manage persistent data in phase change memory. Okay? And there are some tutorials also. There's a very nice workshop, that's the last one that's listed here. It's an annual workshop now that's being held at UC San Diego. It's a fantastic place where I was one of the speakers. In fact, I gave a version of this talk over there last March. I had never seen such a mix of people all the way from chips level to application level people getting together. And they even fund a whole bunch of students to attend this thing because these two guys, one of them is an ex-Almaden guy, managed to get a lot of funding from, I think, NSF to even make students come and do posters even if they're not having full-blown papers to present. And so I found that a valuable discussion. And some of the hardware people who are really working on the chips, when I presented, they're like, oh, I never thought of this and so on. So even systems architecture stuff, forget the real software implication, they are not really thinking about. So this is one of the major things that's happening. And in fact, I'm now part of a group at IBM Research, which is looking at what we call integrated disruptive plays. The head of the research division is really worried that we need to figure out what comes after multi-core. Okay, there was the time when we were all, building more and more powerful single CPU kind of processors with, Moore's law, doubling, blah, 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 all that stuff. And then for reasons of heat dissipation and power consumption, we decided, even though we can still cram more transistors on a chip and such, we shouldn't be using all of that to just build more and more powerful processors or faster and faster processors. Even though we could do that, it's not beneficial to do it. And hence this era of multi-core. What comes next? As potentially we run out of even multi-core giving all the benefits that we are used to in terms of overall compute power and such increasing dramatically, which allows the software guys to be pretty lazy, and hence the bloating of things like Office or whatever software you look at. Every time you turn around and a new release comes out, it wants more memory, this, that, and they're pretty casual. In the interest of productivity, they don't try to deal with the sorts of things that I had to deal with when I had 256K of memory to write my programs in, right? Or even now with the cell phone and such smartphone or smart cards and so on, people don't have the luxury. Or you have a sensor which has Mickey Mouse amount of everything. The battery power available, whatever. So you have new operating systems coming out as it happened at Berkeley. So we need to think about all this differently now and worry about overall stack optimization. As you find that the individual CPU performance doesn't keep increasing as it used to, you now have to, across the whole stack, do the optimizations, make compilers become smarter and so on. Of course, multi-core also brings with it all the headaches of having to write programs that leverage more than one core for any given piece of work that you might want to do, especially if you're going to be munging on a whole lot of data. Now, if the Joe Blow programmer is not really, armed with all the brain power or whatever it is, tools to do the exploitation by programming it in, then you need to have something in between that guy and what executes that does that translation. And of course, this has been a bane of high-performance computing, where forever they've produced all these fancy machines, but they haven't quite succeeded in doing this automatically. And of course, now we have people even in Almaden who have a new language called AQL, where they are trying to do for text what was done for data by traditional parallel DBMSs to automatically parallelize even math functions that are in R and such packages, right? To leverage large number of cores and lots of memory and so on, so that you as an individual doesn't have to worry about how to parallelize these things that might execute for a long, long time. Or you want to be able to make things that are more batch-oriented become interactive. That's the other goal of a lot of the focus on analytics. Things that might have been done in overnight runs, they want to be able to now do in real time. This includes things like fraud detection, or in the case of Wall Street kind of companies, they want to be able to, during the daytime itself, as they are making decisions on loan applications or what to buy and so on, they want to know how much of their money is at risk based on whatever probabilistic modeling and such. They don't want to have too much of the surprises of 2008 coming up. And so for all of those sorts of reasons, there is a great deal of focus on the whole stack being optimized, and that's one of the things that we are working on, and how to maybe do something in the hardware with 3D chips and photonics within a chip and such hardware developments happening. Let's make those chip guys also become aware of what sort of different workloads are there today, what will be there in the future, and then appropriately even come up with things like reconfigurable computer architectures and such. And have a very flexible way of moving things up and down the stack based on what time it is and what sort of operations you are trying to do and so on. So coming back to the storage class memories, the goal is to blur the distinction between disk and DRAM kind of main memory. And so The major feature of the SCM compared to DRAM is the fact that it's non-volatile, and it will have shorter access times compared to disk, and even better than flash memory. And some of this stuff will be realized in the future, not necessarily true right now. Cost will be more like disk by 2020. And of course, the major benefit is that it's solid state, no moving parts, unlike a disk. So you don't have to worry about seek time and rotational delay and all that we all have worried about forever. And so this gives you some more information on what we expect, in particular for phase change memory, one instance of SCM to be. As you probably know, in the case of flash, for instance, write takes a much longer time than read. So there is that asymmetry between read and write compared to DRAM. That will still be true of PCM, okay? Because you are physically actually heating the device to make it do a state change by supplying power. And it's similar to DVD kind of material, okay? And that's what makes the writes more expensive than reads in terms of delay and such. But unlike in the case of NAND flash, which is the more common flash as opposed to NOR flash, which has terrible reliability problems, there are two things, right? Cell endurance and data retention. Endurance is, if you keep rewriting a piece of storage, how long does it continue to work? It's only 10 raised to 4 writes. That's for what's called MLC flash, multiple bits per cell. For SLC flash, which is 1 bit per cell, it's 10 raised to 5. Whereas DRAM, forever works. As long as you have power and you keep reading and writing and whatever, it keeps working. The other one is data retention, which is once you write something, how long does it stay in the correct state? There again, NAND is not all that good. Whereas DRAM, as long as you keep supplying power, it will keep that value forever. I mean, there are, of course, some random errors and all that stuck on 0 or 1 kind of things. But other than that, in general, it's not like the whole device goes kaput. And so it's because of the fact that there is this cell endurance thing. And also in the case of flash, once you have written something, in order to rewrite that area, you have to erase, as they say, a whole block, where a block consists of multiple pages. And then you can rewrite one of those pages. You don't have to rewrite the whole erased block. Because of that also, it takes much longer time to do a write in the case of flash. Whereas in the case of PCM, there is no need for this erase and having to write a whole page. You can write even individual bytes and so on. So it's byte-oriented rather than page-oriented or block-oriented, and no notion of having to erase. So because of all that, there will be significant advantages to PCM. And what's also expected to be the case is, at some point, both DRAM and flash are expected to run out of gas when it comes to scaling. As you have smaller and smaller dimension circuitry, PCM is expected to still function correctly, okay? As you go to the low nanometer scale and so on. Already some chips are available, low density PCM chips from Micron, but they are not yet available in production quantities. They are available in more limited quantities. And to begin with, they've also focused on what's called NOR compatible PCM chips. They wanted them to be drop-in replacement for NOR flash chips that are in some of the Samsung phones and such. They didn't want to wait till the interfaces are standardized for byte-oriented, wider adoption kind of DRAM replacement kind of scenario for PCMs. So there has been some delays in terms of the actual production of the originally announced things like 1 gigabit chip that Micron, for instance, was supposed to ship back in 2010. Micron acquired a company called Mnemonics, which was originally formed between ST Microelectronics and Intel. And Samsung is also quite a player here. But otherwise, there are lots of people examining this space, and that workshop that I mentioned in UCSD, they had lots of people from various organizations over there. There are many other companies that are also hardware-oriented companies in Taiwan. I think there's a company called Hynix, which is also quite active. The whole idea is to, of course, keep moving to the top right corner of this picture, where you are trying to have something that's persistent and also that's very fast, but better than flash as well as disk. The difference between non-volatile and persistent is that non-volatile just says without power it will be there, but because of all those other problems I mentioned, cell endurance and such, in order for it to be really persistent, you need to do duplication and such. So it's because of that problem with, what was it called, endurance, that in Flash, they have this notion of wear leveling, where because they don't want a whole chip to have to be thrown away just because one part of it is no longer working correctly, because that part, because of a skew in the data modification reason, kept getting rewritten too often, and then it went out of gas. So what they want to do is, in spite of the data being in a skewed fashion being modified, they want the device itself to be more uniformly written into. So the way they do that is they have a level of indirection. So they keep remapping the physical place where a logical page at any given time is stored. So by keeping track of how often the real physical pages have been written into, they can keep changing the location of the logical page that's being more often written into. So the logical page 10 may at one point be at physical page 10, it may be at physical page 15, and so on. So as a result, when you are doing writes, there's a level of bookkeeping that needs to be done. This is why it's also hard to do that if you are trying to access it like DRAM, where the latency will be a big factor. So as long as, like in the case of Flash, where you keep accessing Flash even though it's solid-state memory and so on, more like an I/O device, meaning you use asynchronous protocols, the process gets suspended when the flash disk operation is going on. All that then means that there's a great deal of overhead anyway in going and getting a page of data out of Flash or writing a page of data into Flash. So you can afford to do more of this kind of bookkeeping during that operation. Whereas for PCM, that would be much harder to accomplish if you're accessing a few bytes here and there. Okay, so here is a laundry list of the different kinds of SCM technologies that people have worked on. Even in IBM, we have had people working on things like racetrack memory, but the one that's expected to be fairly successful with a lot of promise, with quite a bit of work having been done in a more, seeing the light of day kind of context, is PCM. As I said at the beginning, HP has been pushing on what they call memristor, which is listed here under solid, electrolyte, and resistive RAM. But our guys say there's a lot more that still remains to be proven about that. New York Times actually had an article about this because HP has made so much noise a few months ago. New York Times. Meanwhile, of course, the Flash guys keep hammering away at some of the problems with Flash. And so this is a hard thing to compete with, right? Because there's so much going for Flash. And by the way, what really made Flash succeed quite a bit in terms of killer applications and so on was the wide adoption of, by you and me as consumers, digital cameras, and the other one being all these personal music devices and such like iPod and so on. So those two meant some of these reliability things were not as much of a problem. Yeah, if your music recording gets hosed or your photos get messed up, that's okay because you're not using that flash device as a permanent storage. You still have a backup on a regular disk or tape or whatever, kind of device. Whereas when you're going to now use this more for storing in a long-term sense, if you try to do it for enterprise data and so on, then it's a different story. And that's why enterprise-grade flash is much more expensive than commodity flash. Just like enterprise disks are that much more expensive than commodity class of disks. And this goes back to the point I made about how all these Hadoop kind of people and so on, they are all now in the context of AWS and Google's whatever their thing is called, they are all now after this whole business of El Cheapo processors and El Cheapo disks that are locally attached without the expensive SAN kind of networking infrastructure. Okay, that's okay as long as you are dealing with data that you could afford to lose and so on. But the minute you have higher reliability requirements and such, then you need to look at things very carefully. I've already mentioned some of this, so it should be fairly obvious. It turns out the phase change memory, even though it is usable in a byte-oriented fashion and hence more like DRAM, it could still be used like a disk drive in the sense of accessing a page at a time. And it turns out the hardware guys have a lot of flexibility. Depending on what usage pattern you want to support, they can tweak the hardware parameters, thereby making it cheaper, faster, and so on. Okay? And even the operating temperature is something that they can play with. So let me quickly give you an idea of what it means in the real world time frame sense. When the CPU operates at 1 nanosecond, if you equate it to, in real life, 1 second of time, look at how much of a difference it makes. Accessing a tape is like a century of time being taken. CPU is operating at 1 second, and if you have to go fetch something from tape, that's like having to wait for a century, and so on. So the niche that PCM can fill is in this an hour or so kind of time frame. That's still quite a bit slower than what the CPU is doing, right? Over time, the CPUs have become faster and faster, but the rest of the stack, the memory stack and the disk stack hasn't kept up with it. And there's some information on prices and so on. So here is where you will see some differences between enterprise-grade stuff versus commodity kind of disks as well as flash memory. In terms of hardware architectural alternatives, you can either attach the SCM where the DRAM would be attached next to the memory controller, which means it will be accessed synchronously while the process is sitting there waiting for stuff to be brought. It's twiddling its thumb. Whereas if you attach it to the storage controller, I/O controller, then it's more like async I/O being done, just like the way flash is accessed. Virtual disks and so on are accessed today. And depending on that, you may use it for different things, because you could use it because it's cheaper than DRAM. You could use it as and it's faster than a disk. You could use it as a paging device. There, the persistence of that device is not of any value, unless you're going to use it as a hibernation device, right? Instead of disk, you can use that. And there are already some guys who do that with flash, but with PCM, because of some of the other characteristics, may be a better choice. This is talking still about this stuff that we have already discussed. So in terms of where you might use these guys in the database context, you could, for instance, avoid that object relational mapping that I was talking about. Today we are doing that because the programming language is accessing the data in the volatile space using object primitives. But the data, in order to become persistent, has to be shoved into a relational store, which is not object-oriented. Whereas if the memory in which you are operating on it in the programs, if that memory itself could become persistent, maybe then you don't need to do this OR mapping. Those are some of the sorts of things that people are talking about. The problem with that view is, just like the ODBMS guys had that kind of vision, as long as there is only one language in which you are accessing, you are fine, because the in-memory form is the same as the persistent form. The minute different language programs have to access it, given that there isn't a standard across different languages in terms of data type, hardware representation, in-memory representation, you still need some level of translation to happen. This is what the object store guys discovered when they went whole hog on trying to make the distinction between persistent and non-persistent data access through C++ all be done magically without yourself having to do anything. But then once you said you want to access it through some other language, then they were in trouble. So people are also, in the in-memory context with caching and such, done a number of things over the years, especially in the context of the web-oriented systems. They have used things like memcached as a place to cache persistent data, but then they had to deal with it in a very painful way, because the application had to know that some data is cached in this volatile store using something like memcached, but it had to also deal directly with the persistent store, which was backed, which was front-ended, if you like, by a relational DBMS. So there is a picture, I believe, somewhere here. Yeah. So this is what's happening, right? When you have something like this, which is what lots of these Web 2.0 companies have done, what you would like to do is marry the two, because, oh, I see, I know what they have. So look at all this writes having to be done to both places, or at least invalidation of the cached version had to be done when you modify something that's already in the cache. Reads, of course, will go to the cache, but if the cache doesn't have it, then it has to be pulled out from the persistent store. By merging the two, the hope is that the application can just deal with this one thing, and it doesn't have to deal with both of these things and worry about all the associated headaches. There are lots of projects around that are working on this kind of thing, as well as venture-backed companies. So one of the big projects, for those of you who know about John Osterhout, who worked on the log structured file system. He has been at Stanford now for a while. He did that original work at Berkeley. He has a RAM Cloud project where he said, lots of these Silicon Valley companies are using vast amounts of DRAM memory to do this in-memory management to support the faster response time requirements of Facebook and such. But what's happening is that when you have a huge cluster of machines with lots of memory in each machine in the cluster, in order for you to use all this memory as if it's in one machine, you need to now have much faster inter-processor communication. So the communication stack has to become much more efficient. So that's one of the things that he was doing. Plus, because it's volatile memory, because he was not thinking about using flash or PCM, he also had to worry about the failure handling of individual nodes with the memory contents disappearing. So he has got stuff going on there. We had a project where we were considering various things. I'm rushing now because he's telling me it's time. Various ways in which you might use the PCM. You may just say, I'll use it only as a logging device because it's going to be much faster than disk. With all the increased transaction throughputs and all that, could that then solve my problems with not being able to do enough commits and so on if I'm dependent on a disk? It turns out, as long as that store itself is not a long-term store, you still have to move the log from there to somewhere else. Now, it's a question of pay me now, pay me later. If your real problem is you're cranking out so many log records that you are unable to push it out at the appropriate times to persistent store, then you will get into trouble when you move it from PCM to regular disk or whatever that other store is, which is a long-term storage. If you're going to tell me I'll batch that, whereas here I'm not batching, then you could do the batching even as you do the commits, and that's what group commit and such ideas are there for. And the other possibility is to do in-memory replication of the log. So then you don't even need the persistence if you replicate in enough places, and then you can acknowledge to the user that his transaction committed. Or you can store the whole database, or you can use this as one more level in the storage hierarchy, meaning you have DRAM buffer pools, and then instead of just disk being the next level, you could have a PCM-based buffer pool in between. In that case, the chances are good that you will use it more in a page-oriented way rather than a byte-oriented way. And there are already examples of these sorts of things being done in our traditional database systems. I've given some examples here. So we could leverage that. And as in-memory databases which have been around, times 10 and SolidDB, times 10 was a HP Labs project which spun out as a separate company which got acquired by Oracle. IBM went and acquired a company called SolidDB in Finland. They were also forced to deal with this issue of, can they assume everything fits in memory? What if it doesn't fit? Are you completely messed up? So the same sorts of questions will come up even in the PCM context. Of course, for a given pot of money, you can buy, in due course of time, a lot more PCM than DRAM. At this point, actually, they are more expensive than DRAM, it turns out. So does that make the problem go away of having to deal with yet another level in the storage hierarchy, namely disk? Probably not. And the other problem is, even though this device is persistent, if the CPU attached to it has any problem, then if you don't have an alternate path to that memory, you are messed up until that CPU comes back to life. So this is like, disks which have two servers attached to it, as it's been the case with nonstop SQL and such. Alternate path will get you access from a backup server to that device. The same sort of thing you need to worry about in this context too. So that's what some of this stuff is talking about. And so the question that we were dealing with was, should we design from scratch something? So in this context, what we did was we took memcached, because we didn't want to be bothered with all the SQL-related things which have nothing to do with the specific thing we were trying to figure out, which is how do we leverage the functionality of something like PCM? And so we chose to then, with all the hoopla also with NoSQL, we thought we could have a value add to NoSQL by adding traditional transactional locking and recovery logic, and independent of PCM, that will still have value. So that was the thinking behind us picking that up. Plus, we didn't want to also take SolidDB and such in-memory technology that was originally designed for a volatile memory environment. So we thought that we should have a much simpler starting point so that we can more fully, if you like, from the bottom up, think of how we might design a brand new DBMS without having to do all the more mundane stuff that didn't matter so much. So the storage allocation such that was already in memcached. So that's it.
You want to stop and take a few questions?
Yeah.
I know many of you will have to leave, so maybe we can just stop right now and open the floor for some questions. There will be a reception right afterward in case you would like to spend more time.
Yes, Elisa.
I know, Mohan, you're not the optimizer person, but can you comment on what would be the implication on a query optimizer of this more complex storage hierarchy?
Yeah, so already actually there has been some work at IBM Yorktown Heights where in the context of flash memory, they've thought about and written a few VLDB papers on the notion of keeping track of hot and cold data dynamically and then automatically migrating it between these different hierarchies. And of course, the cost modeling also gets totally messed up, right? Because today we model actually the number of IOs and so on. And the DB2 mainframe models are even more detailed, they take into account what the size of the disk is and what the speed of moving the arm is and rotational delay and such. Whereas in the original system R, they only counted the number of IOs. That's it.
Now also even installing an IBMS may become very complicated because it has to be parametric with respect to the hardware.
Right. They already, over the decades, have been forced to refine and make it even more detailed, all the cost models associated with database query optimizers. And those things would have to now take into account the characteristics of something like PCM. And I'm not sure how much of that has already been done with Flash. But this project at Watson was focused on Flash and those papers that they have. One deals with this dynamic tracking of hot and cold data. And the other one is on if I have fixed amount of this kind of storage versus that kind of storage, like disk versus Flash, how do I distribute my persistent data across those, assuming for the time being that Flash is the permanent store? Should indexes be put in Flash, for instance, and the data be kept on disk, that sort of thing? Of course, it all now depends on the schema, the workload characteristics and so on, how often, what you're accessing and such. Not too different from all the wizards or whatever that are there for dealing with what indexes to define and such, right? They took into account similar kinds of information being provided by the DBMS admin. Well, the recovery logic for sure gets more complicated because if you are actually storing something in a long-term sense on this Flash or PCM device, you clearly have to back up that also on disk and so on. So, and dealing with some of these error conditions that come about means also you need to be able to restore parts of it rather than having to restore the whole thing and such. Any other questions?
What did we like the speaker? Sorry.
Oh, okay, there was one. Thank you.
And we will have time to speak.
Sure.
With Mohan
Thank you.
Here.